first, what is a Wronskian? At its core, a Wronskian is testing for linear independence. And the other way to think about a Wronskian is it's essentially a determinant that determines whether two solutions for a second order linear ordinary differential equation can satisfy the initial condition. The given formula slash equation is W f of g x is equal to the determinant, and you would have a very simple matrix f of x. Then you would have the derivative, first derivative, f prime of x. And then you would have the g of x prime x. And that would be equal to f of x, g prime x, minus f prime x, g of x. Now, if the output of this Wronskian is not equal to 0 at any point, then this shows that f and g are linearly independent. If it shows that this output is equal to 0, then it shows that they are linearly dependent. So if w is not equal to 0 at any given point or any given x, then f and g are linearly independent. So now we're going to focus on the second component on how it's relevant with second order linear homogeneous differential equations. Now, the general solution for all second order homogeneous equations is essentially ay prime double prime plus by prime plus c is equal to 0. Now from here, we can convert this into the characteristic equation. And what is the character equation? The characteristic equation in this context, so it differs, but in this context, it is a simple polynomial equation, which is derived from the differential equation to find its roots. So in other cases, it can be derived to find from a matrix to find its eigenvalues, but converting this into the characteristic equation is just as simple as converting the y double prime into r squared. So ar squared, and then the y prime as r, br, plus c is equal to 0. Now, what I meant to note here is that this is dy is equal to 0. And for a characteristic equation, the y itself will be converted into just nothing. And that is because now we can use this as an algebraic way to manipulate, and via the from the quadratic formula, we can find its valid roots. Now with ar squared plus br plus c, this format allows us to be solved using the quadratic formula. Now the quadratic formula is negative b squared minus 4ac over 2a. Now there are three cases or theorems to find the general solution, and the first one that we're going to focus on is distinct real roots, and there's double real roots. Lastly, there are complex roots. This video will only cover the first portion, so we will eliminate the second and third. But what are distinct real roots? It essentially means that we have R1, R2 in all real numbers, then these are two distinct roots, two distinct values. Now for this case, we can easily find it if it's a distinct real root, or theorem 1, if the discriminant b squared minus 4ac is greater than 0. So if the discriminant is b squared minus 4ac is greater than 0, then we know that roots r1, r2 are in the are in our real numbers, are in the real integer, are two distinct values. And the general solution for that would be y is equal to c1 times e r1x plus c2 times e r2x. Now with this general solution for this particular case, we can apply it with the Wronskian. And now the third step is bridging these two together. So we know what a Wronskian is. We have this determinant, and then we have this matrix thingy looking thing, and then that equals to f of x, g prime of x minus f prime of x, g of x. And we also have the relevance with second order linear differential equation, and we're focusing on the first case slash theorem, which are only distinct real roots. Now the first example is that if we have the distinct real root r1, r2, then this is coming from this right here. We're going to have the general solution to be given as y of x is equal to c1 times e r1 of x plus c2 times e r2 of x. Now this is the same general solution as we have right here from the first theorem. Now, in order for us to prove this, we're going to just prove it logically. If we let y1 of x as equal to e to the power of r1x, and y subscript 2 of x is equal to e to the power of r subscript 2x, so it's going to look like this. And we have two solutions that are not constant multiples of each other. And if they're not constant multiples, then they are linearly independent. Now we're going to use this via the Wronskian. Now y of 1 and we have y of 2. We're going to find the derivative of y of 1. Y of 1 derivative is going to be r1 times e to the power of r1x, and derivative of y2 is going to be x times e to the power of r2. Sorry, I mean r2 times e to the power of r2x. Now we have the following derivatives, and we're going to translate that in terms of f, terms of g, terms of f prime, terms of g prime. For here, f of x is given as e to the power of r1x, and g prime is as followed. So this will be f, this will be g, f of x, g prime of x. G prime of x is going to be r squared, r subscript 2 times e to the power of r2x minus f prime of x, which is r1 times e to the power of r1x. Now g itself is e to the power of r2x. Now we can factor this e to the power of r1x. Actually, what we can do is we can take the r2 and r1, and we do r2 minus r1, group that together, and then we have e to the power of r1 plus r2, parentheses x. Now we have r1x. If we substitute this, if we simplify this distribution, we would have r1x times r2x, which follows this previous step. And now this would be our final output. Now with our final output, we can see that r1 is not equal to r2. Good. And also r2 minus r1 does not equal to 0. So since r1 does not equal to r2 and r2 minus r1 does not equal to 0, and e to the power of r1 plus r2 of x has to be greater than 0. Why is that? Well, simply put, even if x was 0, e to the power of 0 would be going to be greater than 0 no matter what. And looking at this first, we know that this is true. So this cannot be 0. Wronskian for this problem cannot be 0. It is linearly. Now applying it to not the proof, but a viable problem, we're going to consider this equation. Y double prime minus 5y prime plus 6y is equal to 0. Now this general solution, to find a general solution of this, we're going to first convert this into the characteristic equation. Characteristic equation of this would be r squared minus 5r plus 6 equal to 0. We find the valid roots from now here. This is just algebra. And do r minus 2, r minus 3. 2 times 3 is 6. Negative 2 times negative 3 is 6. Negative 2 plus negative 3 is negative 5. Now we have two roots, r2, and r equals 2, r equals 3. And now these roots are distinct real roots. Now if they are distinct real roots, we would use the general solution equation as y of x. Y is equal to c1 times e to the power of 2x plus c2 to the power of 3x. Now this is stemming from this equation right here, c1 times e to the power of first one, r1x plus times e r2. Yeah. So we have the general solution right here. And what do we do with the general solution? Now we have to verify it with the Wronskian. The way we do that is we collect what we have. So the Wronskian is going to be, first set this up, w comma g of x is the determinant. The determinant with f of x, f prime x, g of x, g prime x equal to f of x, g of x, now g prime of x minus f prime of x, g of x. This must not be 0 in order for this solution to be linearly independent. If it is 0, then the solution is linearly dependent. Y of 1 is going to be equal to, as we got here, e to the power of 2x. Y of 2 is going to be e to the power of 3x. Y prime is going to be 2 times e to the power of 2x. And y prime of 2 is going to be 3 times e to the power of 3x. Where we just plug in the values. F of x is y1, which is e to the power of 2x times 3 to the power of 3x minus prime. Now right here, we can see that this is going to be 3 times e to the power of 5x because we can add the powers together since we're multiplying the exponents. So this essentially is going to be 3 times e to the power of 5x minus 2 times e to the power of 5. This just brings it down to 1e5x, which is just e to the power of 5x. And we know that e to the power of 5x cannot be 0 since whatever we put for x would result this into be the exponent be 0. And the e to the power of 0 is essentially 1, and 1 cannot be 0. Now this shows that since e to the power of 5x is not 0 for all x, the two solutions that's given are linearly independent.